Hi everyone, welcome to our discussion in calculus. So for this video, I will be talking about the limits of polynomial, rational, and radical functions. Now, I'm quite aware, or I know that you are already familiar with these different types of functions since you had these discussions before, especially in your algebra. But anyway, just to recall, so if we say polynomial functions, so these are functions composed of various terms. Each term is composed of a numerical coefficient and a certain variable, and it is separated by the operations addition and subtraction. Now, for rational functions, these are functions in the form a over b, wherein b, or the denominator, should not be equal to 0 because that will be undefined. Now, for radical functions, these are the functions that are enclosed or inside radicals or those symbols. So I hope that's clear. So let's proceed. In the previous lesson, we presented and illustrated the limit theorem. So if you can still remember, if you can still recall, in our previous discussions, we have talked about the different theorems in finding limits of functions. So we start by recalling these limit theorems. So we start by trying to review the various or the different limit theorems. So Theorem 1, let C, K, L, and M be real numbers, and let f of x and g of x be functions defined on some interval containing C, except possibly at C. Because as we have discussed before, our function is approaching C, but not exactly C. So the first one, if the limit of f of x as x approaches C exists, then it is unique. Unique in the sense that there is only one limit to a certain function. That is, if f of x as x approaches C is equal to L, and the limit of f of x as x approaches C is equal to M, meaning L and M, or L is equal to M. So just like our discussion before, when we use the table of values, the limit of the function as x approaches C from the left should be equal to the limit of the function as x approaches C from the right. So again, the limits from both sides should be equal. Otherwise, if the limits will not be equal or will not be the same, that will mean that the limit does not exist. Or we simply write D N E. Okay? Let me just erase that. So second one, we have the limit of C as x approaches C is equal to C. If you can still remember, this theorem is what we call as the constant theorem, because again, constants are constants. They will be the same no matter what. Constants, the values will never change. So for example, we have the limit of, let's say 5 as x approaches C is of course equal to 5. Okay, again, the values of the constants does not or will never change. 5 will always be 5 no matter what. Another example, let's say the limit of 30 as x approaches C. So obviously, constant theorem, the limit is, of course, 30. Okay? I hope that's clear. Let me erase that. So third one, we have the limit of x as x approaches c is equal to c. Now we call this theorem the Substitution Theorem because we are dealing with a certain variable x. Now if we say variables from the word vary, the value can change depending on what value we are being given. So let's say, for example, the limit of x as x approaches 9. So by substitution, we can say that the limit is equal to 9. Okay. Another example, we have the limit of x as x approaches 15. So by substitution, that is 15. Okay. So yeah, that's for the third theorem. Next, for number 4, letters A, B, C, D, E, and F. So these are theorems concerning operations. Constant multiple, that's somehow multiplication, then addition, multiplication, division, raising to a power, and extracting the root or functions wherein we have radicals. So letter A, for point A, we have the constant multiple theorem. So here, for the constant multiple theorem, if there is a certain constant before a certain function, all we have to do is to put the constant like outside of the function. Then after evaluating the limit later on, we will be multiplying the constant to the value or to the limit of the function. Let's have an example. So let's say the limit of g of x as x approaches c is equal to 10. Now, if we have the function, the limit of 3 times g of x as x approaches c. So by the constant multiple rule or constant multiple theorem, so we place or put 3 outside or before the limit of the function. So that will become 3 times the limit of g of x as x approaches c. Now we are already given the value or the limit of the function g of x. So that's 3 times, simply substitute. We know that the limit of the function is 10. So simply multiplying, that will give us 30. Okay, I hope that's clear. So the constant multiple theorem is simply placing or putting the constant first outside or before the limit, then evaluate the limit, then later on simply multiply or simplify. Next, 4.b is the addition theorem. So suppose we have the limit of f of x as x approaches c is, let's say, 10. Then the limit of g of x as x approaches c is 11. So if we have this one, the limit of the quantity of f of x plus or minus, it can be addition or subtraction. So f of x plus or minus g of x as x approaches c. So all we have to do is to simply add. So given these two, so if f of the limit of f of x as x approaches c is 10, then the limit of g of x as x approaches c is 11. So simply add both limits. That will give us 22. So it's that easy. Okay. So same thing with subtraction. So if here, if we'll be using subtraction, so simply subtract. So that's minus. So that will give us -1. Okay. Let me erase this one. So letter C, let's have the same given for the limit of f of x and g of x. Next, we have the multiplication rule or the multiplication theorem. So let's look for the limit of the quantity of f of x times g of x as x approaches c. So we already know the values here. So if we have the limit of f of x as 10, then the limit of g of x as 11. So simply multiply. That will give us 110. Okay, so just simply use the operations. Letter D. So letter D is division. So still the same example for the same given. So that's the limit of f of x over g of x as x approaches c. So we know f of x is 10, then g of x is 11. So that's 10 over 11. For your answers, it would be better if you express it in a fractional form rather than decimal form for the value to be more exact. But if your answer can still be simplified, reduced to lowest term, that would be better. Now, letter E. Let me erase this first. Letter E is the power theorem or the power rule. So we have the limit of f of x raised to p is equal to L raised to the power of p, which is a positive integer. So suppose we have the limit of f of x as x approaches c is being raised to the power of, let's say, 2, or we square it. So given this one, the limit of the function f of x, so we know that's 10. Then if we square that one, that is simply 100. Okay. Next. So letter F, that's the root or the radical theorem or our rule. So the limit of the nth root of f of x as x approaches c is equal to the nth root of L for positive integers n, and provided that L is greater than 0 when n is even. So let's say we have this given. The limit of f of x as x approaches c is 100. So if you're looking for the limit of the square root of f of x as x approaches c, so that is simply the square root of 100. Since f of x right here is 100, simply look for the square root, which is 10. So those basically are the limit theorems which we have or which I have tackled or discussed last time. Now for this discussion, we will be applying those theorems in solving or looking for the limit of, again, polynomial, rational, and radical functions. So in this lesson, we will show how these limit theorems are used in evaluating algebraic functions. Particularly, we will illustrate how to use them to evaluate, again, what I have said, polynomial, rational, and radical functions. So we have the limits of algebraic functions. So we start with the first one. We have the polynomial functions. So example number 1, determine the limit of the function 2x plus 1 as x approaches 1. So this function right here, this is a polynomial function. It is composed of two terms. The first term is 2x. The second term is 1. Now, from the theorems above, so using the theorems which I have discussed earlier, so solving for the limit, we can actually apply first the addition property or the addition rule, since the polynomial is separated by addition or a plus sign. So since we know that we will be applying the addition rule, we can actually also apply the distributive property. We can distribute the limit to each of the terms here, 2x and 1. So if you can see right here, we have the limit of 2x as x approaches 1 plus the limit of 1 as x approaches 1. So there. Now, for the first term, we can use the constant multiple theorem. Since we have the constant 2, we put that outside or place that outside or before the limit. So we have 2 right there, you can see. Then evaluate the limit of x as x approaches 1. We can apply the substitution theorem or substitution rule. Since we know that x is 1, so that's why this became 1. And for the second term, since that is a constant, so the limit of 1, which is a constant, is of course 1. Now simplifying 2 times 1, that's 2, plus 1, that is 3. So it's actually like simply basic algebra. All you have to do is apply the rules, apply the theorems, then substitute, then simplify afterwards. Example number 2, we have the limit of the function 2x cubed minus 4x squared plus 1 as x approaches negative 1. So this right here, this function is also a polynomial function. This is a trinomial composed of 3 terms. This is the first term, 2x cubed. Second term is negative 4x squared. Third term is the constant 1. So we can apply the addition theorem since our function, our polynomial function, is separated by plus and minus sign, addition and subtraction. Then again, distributing the limit to each of the terms. So we evaluate the limit of 2x cubed as x approaches negative 1 minus the limit of 4x squared as x approaches negative 1. Then lastly, plus the limit of 1 as x approaches negative 1. So for each of these terms, you can apply different theorems or different rules. So for the first term, 2x cubed, we can apply there the constant multiple theorem and the substitution theorem. So place or put 2 before the limit. Then here, we can apply substitution. The limit of x cubed as x approaches negative 1. Simply substitute negative 1 to our x. So that's negative 1 to the power of 3 or negative 1 cubed. For the second term, still constant multiple theorem, place the constant 4 before the limit. So that's why we have 4 right here. Then substitution, substitute negative 1 to x squared right there. So that's negative 1 squared. Then the third term, since that is a constant 1, so again, the limit of a constant is the constant itself. So that's why we have 1. right there. Simplifying, that's -1. Cube is of course -1 since the exponent is odd, times 2, that's -2. The -1 squared, that's 1, times -4, that's -4, then plus 1. So simplifying all in all, that's -6 plus 1, that is -5, which is our final answer. By the way, if you have questions, clarifications, feel free to ask. Example number 3, we still have a polynomial function. Evaluate the limit of the function 3x to the 4th power minus 2x minus 1 as x approaches 0. So still, we can apply different theorems here. So again, distribute the limit to each of the terms in the function. So we have here the limit of 3x to the 4th as x approaches 0 minus the limit of 2x as x approaches 0 and the limit of 1. That's minus limit of 1 as x approaches 0. So for the first term, constant multiple rule, place the constant before the limit. Then substitution, x to the 4th, substitute x with 0. That's why we have 0 to the 4th power. Second term, again, constant before the limit. Substitute 0 to our variable x. That's why we have the 0 here. Then the limit of a constant, the limit of 1 is, of course, 1. So 0 to the 4th is 0. Then -2 times 0 is 0. 0, that's 0. So we are left with -1 in the end, which is our final answer. So again, I think this is really, really easy for you guys since this is just basic arithmetic or algebra. So now we will apply the limit theorems in evaluating rational functions. So again, rational functions are functions in the form a over b, such that b is not equal to 0, because that will give us an undefined function. So in evaluating the limits of such functions, recall from Theorem 1 the division rule, okay? And all the rules stated in Theorem 1 which have been useful in evaluating limits of polynomial functions, such as addition and product rules. So still, we will be basically applying all the theorems or the rules that we have in solving for limits. So example number 4, the first example for rational functions, we have the limit of 1 over x as x approaches 1. So 1 over x, that's a rational function. Now, first note that the limit of x as x approaches 1 is 1. So since the limit of the denominator is non-zero, we can apply the division rule. So the first thing that we have to consider is to take note that the denominator will not be equal to 0. Otherwise, if the denominator will be equal to 0, we will be applying a different theorem for that, which I will be discussing later. So for now, we will be considering functions wherein the denominators will not be equal to 0. So for this example, evaluate the limit of 1 over x as x approaches 1. For us to solve this or to determine the limit, the first thing that we need to apply or to do is to use the division theorem or the division rule. Now, since we're done determining if the denominator will not be equal to 0, therefore, we can apply the division rule for this. So same with the polynomial functions. We can also distribute the limit both to our numerator and to our denominator. And applying the corresponding rules for each of those, either the numerator or the denominator. For the numerator, since that is a constant, and again, we know that the limit of a constant is still or also a constant. So the limit of 1 is simply 1. Now for the denominator, we have there the variable x. So for that, we can use or apply the theorem wherein we will just substitute the value of x. So since our x approaches 1, therefore x is equal to 1. That is why we have 1 over 1. Finally, for our final answer, we have 1, which is the limit of our function. Next example, example number 5, evaluate the limit of the function x over x plus 1 as x approaches 2. Again, this is another rational function, a function in the form a over b. But first, we should start by checking the limit of the polynomial function in the denominator. You need to make sure that the denominator will not be equal to 0. Otherwise, we will not be able to apply the division theorem. So our denominator is x plus 1. So if we look or evaluate for the limit of x plus 1 as x approaches 2, simply apply still the limit theorems, substitute x by the value of 2. So that's this one. And distributing the limit for the second term, we have there the limit of 1 as x approaches 2. Now, by substitution rule, for the first term, the limit of x as x approaches 2, that is 2. And the limit of 1, which is a constant, is of course 1. Now, finalizing, adding, that's 2 plus 1, that gives us 3. Now that we are able to determine that our denominator is not 0, so we can go ahead and proceed with applying the division rule. Now, we need not solve for the denominator since that's already done. We already know that our denominator is 3, which we have solved earlier. So we only need to solve or evaluate the limit of our numerator. It so happens that our numerator is x. So applying substitution rule, that's the limit of x as x approaches 2. So substituting x with 2. Therefore, the limit of the function is 2/3. Okay. Next example, we have here the limit of the quantity of x minus 3 times the quantity of x squared minus 2 over x squared plus 1 as x approaches 1. So again, first thing that we have to do is to determine or to know whether or not our denominator will be equal to 0. Because again, if it's 0, we won't be able to apply this certain theorem. So evaluating the limit of the denominator, distributing the limit to each of the terms, x squared and 1. The limit of the first term, the limit of x squared as x approaches 1. That's simply substitution. That's 1 squared. That gives us 1. Then for the second term, that's the limit of 1 as x approaches 1, which is a constant. That's 1. So 1 plus 1, that gives us 2. And of course, 2 is not equal to 0. So we can go ahead and proceed. So same with the previous example, we need not solve for our denominator, or you can just actually copy that one here below since we already know that one. All you have to work on is on our numerator. Now for the numerator, distributing the limit to each quantity. So we have here the limit of the first quantity times the limit of the second quantity. So that's multiplication rule. Now, we still need to simplify further. So we can distribute the limit to each of the terms in each quantity. So that's why we evaluate the limit of each term. So the limit of x as x approaches 1, so substitution, that's 1 minus the limit of 3 as x approaches 1, which is a constant. So that's -3 times the quantity of the limit of x squared as x approaches 1, that's substitution. So that's 1 squared, or simply 1. Then last term, we have the limit of 2 as x approaches 1, which is a constant. So we have -2. So simplifying, 1 minus 3, that gives us -2. Then 1 squared minus 2, that gives us -2 still. -2 times -2, that's +4. +4 divided by 2, that is, wait, 1 minus 3, that's -2. Oh, I'm sorry. Here, that is -1. I'm sorry. -2 times 1, that's +2. So +2 divided by 2. So that gives us 1. Therefore, the limit of the function is 1. So again, it's just algebra. All you have to do is to use the theorems, apply the theorems, substitute. Then for the constant, the limit of a constant is the constant itself. So let f, we have another theorem, Theorem 2. Let f be a polynomial of the form. So this one, f of x is equal to a sub n x to the power of n plus a sub n minus 1 x to the power of n minus 1 plus a sub n minus 2 x to the power of n minus 2 plus and so on, a sub 1 x plus a sub 0. So if c is a real number, then the limit of f of x as x approaches c is f of c. So that's merely substituting the value of c to our function. So all we have to do is to substitute the value of c to each of the given variables in the function. So example 7, evaluate the limit of the polynomial function 2x cubed minus 4x squared plus 1 as x approaches -1. So note first, our function, this function is a polynomial composed of 3 terms. So that's a trinomial. Computing for the value of f at x is equal to -1, we get, so that's substitution. So f of -1. So that x cubed will become -1 cubed. X squared will become -1 squared. That's it. And further simplifying, -1 to the power of 3. Of course, it's -1 because the exponent is odd. -1 squared, that's 1. The exponent is even. So simplifying 2 times -1, that's -2. Minus 4, that is -6 plus 1. That gives us -5. Therefore, from Theorem 2, the limit of the function as x approaches 1 is -1, is equal to f of -1, which is equal to 5. This is the same with our previous topic, evaluating the limit of a function at c versus the value of the function at c itself. So note that we get the same answer when we use limit theorems. Theorem 3, we have let h be a rational function of the form h of x is equal to f of x over g of x, where f, g are polynomial functions. So if c is a real number and g of c is not equal to 0, then we have the limit of h of x as x approaches c is the limit of f of x over g of x as x approaches c is equal to f of c over g of C. So we can apply, this means to say that we can apply mere substitution, but just make sure that the denominator G of C will not be equal to 0. Okay. So applying that theorem, for example, number 8, we have this function. So evaluate the rational function 1 minus 5x divided by 1 plus 3x squared plus 4x to the fourth power as x approaches 1. So all the variable x's will become 1. So here, that's 1. X squared, that's 1 squared. X to the fourth, that's 1 to the fourth power. So 1 minus 5, that's negative 4. Then 1 plus 3 plus 4, that is 8. And simplifying for our final answer, we have negative 4 over 8, or in lowest term, that is negative 1/2. So next, third function that we will be dealing with in this discussion, we will now evaluate limits of radical functions using the limit theorems. Again, this is just very easy. So evaluate the limit of the square root of x as x approaches 1. So note that the limit of x as x approaches 1 is 1, which is greater than 0. Therefore, by the radical root or the radical root rule, we have mere substitution, or using the radical rule, that's the limit of the square root of x as x approaches 1. That's equal to the square root of the limit of x as x approaches 1. So substituting 1 to our variable, that's simply 1. The square root of 1 is, of course, 1. Next example, we have evaluate the limit of the square root of x plus 4 as x approaches 0. So take note that the limit of the function x plus 4 as x approaches 0 is equal to 4, which is greater than 0. So take note, the value cannot be lesser than 0, because if that will be negative, that will be an imaginary, because the square root of negative numbers are imaginary numbers, and we are after real numbers here. So substituting or simplifying, that's the limit of the square root of x plus 4 as x approaches 0. So that's equal to the limit, or I'm sorry, that's equal to the square root of the limit of x plus 4 as x approaches 0. So substituting, so x will become 0. So we will be left with 4. The square root of 4 is basically 2. Next, evaluate the limit of the cube root of x squared plus 3x minus 6 as x approaches negative 2. So since the index is this one right here, the index of the radical sign is odd, we do not have to worry that the limit of the radicand is negative. So it's fine even if the limit will become negative, since anyway the index is odd. But if the index is even, square root, fourth root, sixth root, so that's when we have to check that the radical or the root should be greater than 0 or not negative. So therefore here, the radical or the root rule implies that the limit of the cube root of x squared plus 3x minus 6 as x approaches negative 2 is equal to the cube root of the limit of the function. Now substituting negative 2 squared there, that's 4. 3 times negative 2, that gives us negative 6, and copying negative 6. So that's the cube root of 4 minus 6, which is negative 2 minus 6, that's negative 8. The cube root of negative 8 is negative 2, because negative 2 times negative 2 times negative 2, that is equal to negative 8. I hope that's clear. Next example is a combination of rational and radical functions. Our numerator is a radical, our denominator, I'm sorry, the whole function is a rational function. So again, we have to check first whether or not the denominator will not be equal to 0. So here, that's solved already. The denominator, the limit of the denominator is -5, which is not equal to 0. And for the numerator, the limit is greater than 0. So we can apply the division and the radical root rule or theorem. So since everything has been solved, we can actually go ahead with our final answer. So for the numerator, that's the square root of 9, which is simply 3. For our denominator, that is -5. So for our final answer, that's -3/5. So you can actually check here. You can actually solve for the limits on your own. But anyway, I think that's very easy. So next we have intuitive notions of infinite limits. This concept we can apply in the event that the denominator of rational functions will be equal to 0. So we investigate the limit at a point C of a rational function of the form f of x over g of x, where f and g are polynomial functions with f of c not equal to 0. So the numerator cannot be equal to 0 because if both numerators and denominators will be equal to 0, that's an indeterminate function. So here, our only restriction is that the numerator will not be equal to 0. It's okay for the denominator to be equal to 0, but it's not allowed for both of the numerator and the denominator to be 0. So note that Theorem 3 does not cover this because it assumes that the denominator is non-zero at C. So now consider the function f of x is equal to 1 over x squared. So note that the function is not defined at x is equal to 0. So meaning, if we substitute 0 to our denominator, the function will be undefined. But we can check the behavior of the function as x approaches 0 intuitively. We can first consider approaching 0 from the left. So we go back to our table of values, which we have discussed before. So let's pick or choose values from the left that is going closer and closer and closer to 0. So from the left, we have the values -0.9, -0.5, -0.1, -0.01, -0.001, -0.001, and so on. Again, values that are closely approaching 0 from the left. And if we try to substitute those values to our function, these are the answers that we will get or that will yield. So if you can observe, try to observe, the values are getting larger and larger. Observe that as x approaches 0 from the left, the values of the function increases without bound. So when this happens, we say that the limit of f of x as x approaches 0 from the left is positive infinity. So that is, in symbols, we write the limit of f of x as x approaches 0 from the left. Again, that little negative sign on top of 0, that's read as from the left. X approaches 0 from the left is equal to positive infinity. So again, that's positive infinity because the limit of the function increases without bound or is getting larger and larger. Now, let's try to investigate using table of values now from the right side of our function. So we pick or choose values that are getting closer and closer to 0 from the right. So that's 0 0.9, 0 0.5, 0 0.1, 0 0.01, 0 0.001, 0 0.0001, and so on. And substituting those values to our function, these answers will yield. So still the same thing with the values from the left. The values tend to get larger and larger. So again, as x approaches 0 from the right, the value of the function increases without bound. And so the limit of the function as x approaches 0 from the right, again, that plus sign or positive sign right there indicates that the values are from the right side. So it's also positive infinity. So since the limit of the function as x approaches 0 from the left is equal to positive infinity, and the limit of the function as x approaches 0 from the right is also positive infinity. So therefore, we can conclude that the limit of the function as x approaches 0 is equal to positive infinity. So that's using, again, table of values. You can use your calculators. You can substitute those values. You can try to recheck. So now consider the function f of x is equal to negative 1 over x squared. So note that the function is not defined at x is equal to 0, but we can still check the behavior of the function as x approaches 0. Intuitively, we first consider approaching 0 from the left. So the same thing with what we did with the previous example. So you can choose these values from the left side of the equation or the left side of the function. So as x approaches 0 from the left, the values decreases without bound, or it tends to decrease. So we say here that the limit of the function as x approaches 0 from the left is negative infinity. Because if you continue further, if we use other values such as this one, if you substitute that on your calculators, we will be able to get lesser and lesser or smaller number compared to the previous one. So therefore, the limit of the function as x approaches 0 from the left is negative infinity. Now, from the right side, so approaching 0 from the right, still the same thing. The limit of the function as x approaches 0 from the right is also negative infinity. So therefore, since the limit of the function both from the left and from the right side are the same, so the limit of the function as x approaches 0 is negative infinity. So we now state the intuitive definition of infinite limits of functions. So the limit of f of x as x approaches c is positive infinity, denoted by this one, if the value of f of x increases, so increases without bound, so which is getting larger and larger, whenever the values of x get closer and closer to c. Now, the limit of f of x as x approaches c is negative infinity, denoted by this symbol, if the value of the function decreases without bound, whenever the values of x gets closer and closer to c. So we have one last example right here. So by simply looking at the graph of the function, we have the function 1 over x. So this is the graph of our function. So if you can see right here, as x approaches 0 from the left side of the equation, so the limit of the function decreases without bound. It's getting, the value is getting smaller and smaller. Whereas from the right side of the equation or the function, as we can see in the graph, the values gets larger and larger, that's increasing. So from the left, the limit is negative infinity. from the right, the limit is positive infinity. And since we were not able to get the same limits, therefore we can conclude that the limit of the function does not exist. Okay, that's basic. If the limits are not equal, so therefore the limit does not exist. So we have here two remarks. Number one, remember that infinity is not a number. Okay, it holds no specific value. It has no value. So the limit of f of x as x approaches c is equal to positive infinity, or the limit of the function as x approaches c is equal to negative infinity, only describes, take note, only describes the behavior of the function near x is equal to c, but it does not exist as a real number. Okay? For number two, whenever the limit of the function as x approaches c from the right is either positive or negative infinity, also from the left, we normally see the dashed vertical line x is equal to c. So this is to indicate that the graph of y is equal to f of x is asymptotic to x is equal to c. Asymptotic meaning it only gets closer and closer and closer, but it never touches it. Okay? Meaning the graphs of y is equal to f of x and x is equal to c are very close to each other as x values approach c. So in this case, we call x is equal to c a vertical asymptote of the graph of y is equal to f of x. So here, where's the asymptote? So here we see, so we can see the graph of the function gets closer and closer to 0. If you extend that to 1, it will get closer and closer to 0, but it will never touch 0. So I think you're familiar with the concept of asymptotes since that was already discussed to you, maybe when you were in junior high or in senior high. So we have here solved the examples. You can try to study those examples. You can try to practice on your own for you to better master and understand the concepts or the topic. So we have 12 solved examples. So that's it for my discussion again about limits of polynomial, rational, and radical functions. If you have questions, clarifications, you're always free to ask. So thank you so much for your time. Thank you so much for listening. I hope that you have learned something in this discussion. So that's it. You take care always. Bye-bye for now.